theme. So Mark, thank you so much for coming and giving the inaugural lecture in our In Theory seminar series. We're very much looking forward to your talk, and the floor is all yours. Thank you.
Thank you, Marcus. It's a great honor to be invited to give this inaugural lecture, and I love the title of this seminar series, because if you go out into the community and people ask you what you do, and you say theoretical physics, they say, theory. You mean not actually true. And we're guilty of this ourselves, right? We say, okay, in theory, this should happen. But actually, the theory should stand by itself. It might have realizations immediately, it might have realizations later, or it might just be a self-consistent thing. But the theory should stand by itself. Now, so I'm going to be talking a lot about symmetry. And if you go to any popular book on symmetry, you will. If you go to any book on symmetry, like classic Hem and Weil book on symmetry, you will see stuff like this. Okay, and it looks beautiful, but really, what you're not seeing symmetry here. Really, you should see this, right? I mean, this structure here has all the symmetries you can imagine. I mean, it looks the same in different positions. It looks the same in different directions. It's like the cosmological principle, uniform, isotropic, and so on. This has a lot of symmetry. This has a lot of order, has a lot of structure. This thing here, it has very particular directions that you have to go in order to see symmetry. You can only go out along here, or out along here, or out along here. This thing here, it breaks almost all of the symmetries of this structure here. So symmetry and order are basically inversely related. To go from a highly symmetric object to develop something with structure, we have to sort of typically break some of those symmetries. Now, when we learn physics, mathematics, all the way basically from kindergarten, it's hammered into us we should exploit all the symmetries of a theory, right? So, something is spherically symmetric. We should only use radial coordinates, and we should forget everything else. Otherwise, you're just kind of stupid working out everything and all possible unnecessary variables and so on. If something is, smooth, then you should only be using differentiable functions and, analytic functions and so on. You shouldn't consider anything else. But this can lead us highly astray. And the reason for that is related to this phenomenon of development of structure. And the development of structure arises from certain classes of problems where you maybe minimize something with some constraints, do various things to find a solution of a given problem. Or in physics, we would call it a ground state or the vacuum, things like that. And in that process, rather surprising things can happen, which lead to structure. So let me give you a very, very elementary example. This one is called, is that bright enough? Seems to be. Maybe can we lower these lights here? So this one is called the opaque square problem. So it's a very simple problem. You have a square like this, and you want to, imagine that you want to block light that goes from any edge to any other edge on this square, okay? It's not a mirror, but it's something that will block any such path. So, and you're asked for the structure that has the minimal length that will achieve this task. Okay? So, for example, you could go around all four edges of the square. That would have length 4. That obviously does the job. You can have 2 diagonals because that will block light goes from here to here, here to here. Any edge to any other edge will intersect this this opaque mirror. Or you can imagine that there's a fiber optic cable just sitting under the surface there, and you want to make a trench that locates this fiber optic cable, but the trench of minimal length. Now, so this one's length 2 square root of 2. Now, if you've seen anything like soap films, minimal surfaces, things like that, you'll immediately think of putting in an extra vertex in this structure. So you have something like this. Okay? So a vertex here and a vertex here with a nice 120-degree threefold symmetry at each vertex. And that has length 1 plus square root of 3. So it's smaller than 2 square root of 2. So what is the minimal solution for this problem? It's not either of these, but it's a rather surprising one, and it has a structure like this. So it has a vertex, something similar to the one we saw before, but it has a line which freely terminates in the middle. And once you see a structure like this, you can work out what this angle has to be. It's like 15 degrees, and you want to put a vertex there, and then you can just use calculus and work out the lengths. And it comes out to a nice number. It's root 2 plus root 3 halves, which is 2.639. So if you square this and square the earlier one, 1 plus square root of 3, you'll see they differ by 0.05 or something. Quite large. It's 3.4% better, lower length solution than the one I showed you. Now, the square has 8 symmetries, right? It has 4 rotations by 90 degrees, and it has 4 reflections. This solution breaks 7 out of those 8 symmetries. So it only has now a reflection about this diagonal. Everything else is gone. By the way, these kinds of vertices in graph theory originate with Torricelli, internal vertices, Steiner and graph theory and so on. They're very important, internal vertices in systems. Not only does it break 7 out of the 8 symmetries, but it also changes the topology. This is a disconnected graph. It has 2 disconnected components. So just by solving this problem, you have an emergent, non-trivial topology from a very trivial kind of topological beginning. Yeah, there was a question? Yes.
It's true that this particular solution breaks the symmetry, but at the same time, we would have like 4 equivalent solutions such as rotating.
At the same time, can you speak up a little bit?
That we could cook up another 3 solutions that just rotate in it.
Yes. So you can go from one solution to another solution by rotations. Those are distinct solutions of the problem, though. Mm-hmm. And in general, when you go to like continuous systems and so on, there can be an energy separation between those two, there can be a barrier between those two, so that they don't actually communicate with each other. For example, in field theory, we have an infinite number of degrees of freedom. Each distinct solution is a distinct ground state. They don't mix up. So it's true, you can have then a set of ground states that are related by symmetries. But the each individual solution breaks a lot of the symmetries. Is that clear? Yeah, that's a very good point. Oh, man. Here's another case. This is a problem studied by Newton called minimal resistance problem. So Newton was interested in a projectile moving through very, very low viscosity air, for example, air with just one molecule which bounces off the front of the surface like a train. Imagine the profile of a train. And so when it bounces off, there's momentum transfer and there's a drag. And Newton wanted to work out the shape of this profile that gives a minimal resistance. This is solved in the very end of the Principia, one of his last theorems in there, and it's one of the most difficult and involves, as usual, a lot of geometry and reflection angles and cosine squared of these angles and trying to then relate that to velocities and relate it to drag. Now, Chandrasekhar wrote a book trying to reproduce all of Newton's theorems in Principia, and this one is the most difficult. A bit later, it was translated into a calculus of variations problem, and you can write the drag in terms of an integral over a disk here of 1 over 1 plus the gradient squared of the profile. So now you see that it might be good to have some places where this gradient is very, very large, diverges. Means you might want to have some sharp points in the solution. Now, Newton assumed, it's kind of natural here, that the solution should have radial symmetry. Okay? And then he showed, if you have something spherical, it has half the drag of something that's blunt and so on. But this was studied a little bit later, the early 2000s, by these two mathematicians, Lachambre-Robert and Pelletier in Paris. And they showed that actually there are lower drag solutions, lower resistance solutions that are not radially symmetric. And in fact, the solutions depend on the aspect ratio, that is the size of the front compared to the width like that. Imagine a cylinder with a profile at the front. And the solutions go from, with a fairly large aspect ratio, they develop a blunt face, then they develop a face like a chisel, then they develop a face which is triangular. You can see here this is triangular, then this is square, and you get n-gons all the way down as the aspect ratio gets smaller and smaller, and these are clearly not radially symmetric, and these have a lower resistance than the smooth solutions. So this is exploiting this sharp gradients to minimize resistance at some localized set of points. Yeah. So this is an example of a very smooth looking regular problem, this nice profile, minimize the resistance and so on, where the solutions are very kind of sharp, rough, rather unexpected. And I'll give another example of that which occurs in a soft kind of condensed matter setting. And then just for fun, there's this other problem. Does anyone know about the moving sofa problem? So this problem is very simple. You want to have a sofa. You want to find the shape of a sofa that can be transported along this corridor, turn 90 degrees, and transport this down. Purely two-dimensional. Okay, so you're moving the sofa around. So again, this is the kind of problem where, like the first opaque square problem, where you have a kind of a double minimization problem. You're finding a structure which minimizes some property which achieves a certain task. That's the function. Here you have to determine not just the shape, but the shape of maximal area that does this function. So you can have a square like that. Obviously you want to have something semicircular to help you get around this corner by rotations. That has area pi over 2. And you can do a little better. It was conjectured that you want to have this kind of keyhole shape to get around the corner, but you might want to extend this kind of shape, rectangular, and put in other pieces here. Now this was a problem, unsolved until basically this year. And this year, it was solved by this guy, Gineon back, or 2024. And the structure has gradients pretty much like this, but it looks like this, and it has actually 17 different segments along this boundary. There's the keyhole kind of thing, but you see it's curved there, it has something, little different behavior here, and at all these points. So again, and the area is 2.2195. So again, very simple problem, but with double minimization, minimizing an area, a shape that minimizes an area that does a certain job. And these are very common problems where you want to understand why things develop the kind of shape that they do. So this brings us back to this issue of how shape is determined. In general relativity, we know that matter can drive curvature of space-time, and that curvature can itself dictate the equations of motion for the matter. And we have very similar flavored problems in condensed matter physics, where you have some structure, some order, some field, a spin, a liquid crystal, we'll talk about, things like that, that live on some surface, say, and they have to minimize some energy functional. That energy functional depends on the surface, it depends on the metric on the surface, it has derivatives that depend on the metric. So you have to know what the manifold is before you can even write down the energy functional, and yet you're trying to minimize the functional to determine what that manifold is. So that's a very, very rich kind of problem, and very, very challenging problem, and it can lead to rather unusual solutions of the kind that it sort of gave the flavor of in those earlier examples. So let me take a specific example. This is an example with a liquid crystal. So a liquid crystal, the field that you're trying to describe is an orientation. So liquid crystals are like, say, rod-like molecules that like to, in an ordered phase, like to line up. So you have a field, let's call it N, and I'm going to take it living on a surface which has the topology of the two-sphere. If you make holes in the surface, that gives you a line tension which tends to close up to minimize energy. So it's quite natural to assume that the topology is just a two-sphere. And if you want to write down the Hamiltonian for this system, you'll have a Hamiltonian that involves the liquid crystal part itself. And it's written in terms of derivatives of this order field, usually called the director, living on the surface. And then you'll have a term that controls the shape. The shape is determined by how the surface is embedded in the three-dimensional space it's living in. So that is controlled by something called the mean curvature, and it measures how, at any given point, how it might be curved over this way or curved in the transverse direction, and you sum up those two curvatures and you square them, and this gives you a bending energy term, the integral of the mean curvature squared. A term which was discovered in Paris in the 19th century by a French mathematician. Woman. And so you see here that this term here involves a covariant derivative of the director field squared. That covariant derivative can change because the order is changing, or it can change because you're moving around on the surface. So the order changing is picked out by the ordinary derivative, but you have a connection on the surface as well, which tells you how the things change because you're moving around on the curved surface. So now, how are you going to solve this problem? Why does this keep disappearing? How are you going to solve this problem, because you can't even write down this Hamiltonian without knowing what the metric is, which determines the curvature here. And so you can't even, you have to determine the manifold so you can determine the connection, so you can write down the functional that you're trying to minimize. Okay? That is very challenging. However, you can finesse this problem by asking what you need to do this. What you need to do this is to have the field being very uniform. So uniform means everything is lined up for this liquid crystal. The director field is all lined in a particular direction. And you need it to be flat, because otherwise you pick up, so that will, if it's uniform, that will kill this derivative here of n. But if it's flat, that will kill the connection piece. Okay? So now, you want it to be uniform, which sounds good, and you want it to be flat. But I specified that the topology was that of the two-sphere, which means that there's an integrated Gaussian curvature on the surface is non-zero. That is large. It's 4 pi. So it cannot be flat. everywhere. Okay. So you do the best you can. You make it uniform and flat as much as possible on the surface. So what that means is you want it to be faceted. So you want to have a lot of flat faces, uniform on each flat face, and concentrate the curvature at very specific points. And you can do this in the following way. So here's the constraint. I'm taking the case where the coupling constant that determines the liquid crystalline energy is bigger than the bending rigidity. So you're first trying to minimize the liquid crystalline order. That can be 0 if it's uniform and flat. So here's a way you can do this. As I said, make it flat as much as possible. So you can take a grid like this, tessellation. You just have uniform director field. These are like ridges across the surface, and then you fold it up into a tetrahedron. On each face, the liquid crystalline energy is exactly 0, and you notice these lines continuously connect across here, so there's no problem going from one face to any other face. And the only bending energy occurs across the ridge, which is basically a set of points of dimension 1 in this two-dimensional surface. So they make a very small contribution to the total energy of the system. So here, the solution in this limit is a very, very sharp object. So I was going to pull this out before. Where did I put it? Somewhere in here. I'm going to get it out. Yeah, there it is. Solution is this tetrahedron here. Very sharp vertices, very sharp edges, and liquid crystalline energy is 0, and some bending energy across the edges. And the limit with the bending energy, bending rigidity, that thing kappa in front of mean curvature squared goes to 0. There's even no bending energy contribution. Notice also that, so all the curvature here is at these 4 vertex points. Notice also if you why does it keep doing this? Notice if you go around at one of these vertices, the director field rotates by 180 degrees. So that means that this is what's called a defect for the liquid crystal. It's making a contour around here will have the liquid crystal rotate all the way back to itself, but going around 180 degrees. So this point here is also a point where the liquid crystalline order has to go to 0, where the system disorders. You can see these kinds of structures on the ridges of your fingerprints. This kind of comet structure is a defect in ridge patterns. They're called loops on your fingerprints. And here you have 4 of these defects concentrated at the points where also the Gaussian curvature diverges. So that's what both these vertices are all points where it's kind of disordered. Singular curvature, singular derivatives of the gradient of the director field. And those two things, most best kind of optimal way of solving these problems is to put those two kinds of singularities at the same point. So again, looks like a very, very smooth problem that has very, very sharp solutions. Any questions about this? Yes?
So why would the solution not be any other polyhedron?
Okay, very good point. So if you want to specify a surface, you need more than 3 points. Otherwise, you can have some collinear surface going through it, and you won't make the topology of the two-sphere. So you need at least 4. Then you have to count degrees of freedom. So 4 is the minimum number that you need. If you go to you can have higher polygonal solutions, but then the kind of order that you get on the surface has to match the structure of a face. So for example, if you go to a cube, the faces will be square-like, and the laying down the order on the square would have to have a 4-fold order. So that would occur if your beginning order was not just a line like the liquid crystal, but a cross. And if you go up to triangular order, it will like to live on an octahedron and so on. So you can actually get all of the other polyhedra by changing the basic kind of field that's living on the surface. Yeah. So you can generate all these structures simply by controlling the matter. And that will tell you that the surface should expel curvature, go flat, and have 0 order corresponding to the kind of field you put on the surface to make the right kind of face. So if you have 4-fold order, it should spontaneously form a cube. If you have 3-fold order, it should spontaneously form an octahedron. And the other constraint is that the charges associated with these defects should all add up to the charge, the Euler characteristic of the two-sphere, which is 2. So this has the right kind of defect for a liquid crystal. The higher order symmetries give you the appropriate defects that have different charges. Yeah, good question. So 4 is the minimal solution, and it corresponds to the right one to have these kinds of ridge patterns, which is associated with the symmetry of a liquid crystal. Excellent question. Yes?
Sorry, can I go back to
Yes.
the formula of the Hamiltonian?
Yes.
So how does it change the like you said it depends on like the 4-fold versus 3-fold. Where does how does it look like?
This field N is a line field. So so that means that its invariant under N goes to minus N, inversion symmetry. That's the 2-fold order. If I took N to be a different kind of field, for example, a cross, okay, then that would reflect in this kind of thing, would have to have 2 directions with that kind of symmetry. So it's all dictated by the matter, if you want to put on a kind of field. Yeah.
Thank you so much.
Yeah. Yes, Ira.
Are there 2 couplings there, 2 different
Yes.
moduli?
Yes. So here is the liquid crystalline coupling constant, the Frank elastic constant, and here's the bending rigidity.
So you made no assumption about the ratio?
I did. I said that I take this.
Oh, okay.
I take this limit.
Okay.
So in this limit, you're trying to first minimize this liquid crystalline energy, and that's what makes it want to be uniform and flat. If you take the other limit, where the bending rigidity is very large, then you'll get a perfectly round two-sphere, because it won't want that minimized. That's a minimal kind of surface, minimizing mean curvature squared. Yeah, so you can go all the way in between by simply controlling the ratio of these 2 coupling constants, which
What
is.
does it look like when they're exactly equal?
If you go from infinite bending rigidity and lower it, they'll sort of go out to be ellipsoidal, and then it'll start to go piecewise flat with rounded ridges. So that's what if you start with the solution I gave here, and decrease the ratio of k to kappa, increase the bending rigidity, these will round out. These will round out and eventually go all the way to a round two-sphere.
But the number of vertices is still remain 4.
Yes. Well, when you go perfect two-sphere, they've all gone. The vertices will also round out in that case. Yeah. Correct. So there's just one dimensionless number that controls all of these shapes, merges out of the same free energy or Hamiltonian. And the interesting thing is here you can actually make these things in the lab. And this is how I got involved studying this problem. The polymer chemistry group in Paris who made vesicles from block copolymers, and they can build into these vesicles liquid crystalline order. So it has liquid crystalline order on a spherical shell, and then they image that with electron microscopy, and they show these sharp kind of vertices, corners here. And that is, our theory was that this is a projection of this tetrahedron here. It's somewhat rounded out, you see, onto 2 dimensions. So that's the nice thing, you can check all of these ideas in experiments. Now, let me come to another idea, and that is that normally, yes?
Just related to the image you show us.
Yes.
So was that done like theory first, then experiment, or was experiment and then theory first?
Damn, so this was the case where the experiment came first. Yeah. I was on sabbatical in Paris, and my friend Jean-Paul Joanny said, oh, these polymer chemists have this weird experiment they can't explain, and then we studied it that way. So I prefer it when the other way around, which has happened. But in this case, experiment came first, which is also very valuable. And so, yes.
Sorry, why is it round like that? Why is it
Oh, so this is in the limit of some intermediate ratio, as Ira was asking, of the Frank constants to the bending rigidity. Yeah, so this is a finite bending rigidity, so it doesn't want to be completely flat. Yeah. Now here's another class of problems that are very interesting. Normally, when we heat up a system, we'll disorder it. Okay? So we're used to, say, high temperatures or some parameter varying usually a temperature, which will take you from an ordered phase to a disordered phase. So it will take you from a phase with some kind of a symmetry breaking to some phase which restores the symmetry breaking, or for a phase which has some order to a completely disordered phase. But we might be interested in the opposite thing happening. This occurs if you want the order to persist for up to, say, very high temperatures, then you want a kind of inverse phenomena where maybe the order is created from the disorder. So as you try to disorder the system by somehow, say, heating it up, it will order. This kind of situation where you get more order at higher temperatures where you nominally disorder it is known in quite a few settings. There are salts, for example, Rochelle salts, where as you heat them up, they go to something that's more ordered rather than less ordered. There's the Pomeranchuk effect in helium-3, where the solid phase of helium-3 has higher entropy than the liquid phase. So you heat it up and it can solidify. If you are working on, say, quantum computing, or you're designing systems where you have some set of spins and you have to map it onto a physical layout of qubits, then you need structure in the array of spins and in the physical qubit layout to make that work, to make that mapping through codes and circuits and so on. And so you want that structure to survive to basically as much noise as possible, preferably all the way to infinite noise, in order to preserve this kind of mapping to make it work. So you also need, in that situation, they're interested in the order persisting to high temperatures. And I want to show you, I should keep moving faster. Okay. So I want to show you another example of where this occurs, which involves what's called an elastic membrane. So now we have a two-dimensional surface, a membrane, but on this surface we have two kinds of contributions. So again, we have a Hamiltonian not now with a liquid crystalline order, but with some kind of elastic order. In other words, it's going to cost energy to stretch this membrane or shear this membrane, and it's going to have also this bending energy. It's going to cost energy for the membrane to have some shape in the three-dimensional space that it's living in. Now, if you take a surface like this, you can construct normals to the surface, and normals to a surface look like spins. So you can imagine this system should behave like a two-dimensional ferromagnet. But it's well known that two-dimensional ferromagnets never order. Spin waves will always disorder a two-dimensional ferromagnet. You can't have long-range order for continuous symmetries in purely two dimensions. But this system is a bit different, because the normal to a surface like this is not a simple vector. It is a vector that doesn't have all the rotational symmetries of the space it's living in, but it has to have, it has to be invariant, it has to be actual normal to an underlying two-dimensional surface. In other words, if you move around in this surface, the normal does not change. And so you have to mod out by rotations in the plane of the membrane. So this means it's a constrained vector field. It's got to live on what's the normal bundle of the surface. And those kind of constraints make it a qualitatively different system from the ferromagnet. And the effect of this constraint is that when you heat up the system, it's going to form interesting topographies. And when you deform the shape, there will be stretching induced. When you deform the shape, you necessarily have to stretch the system, because there's a contribution not only from the in-plane stretching, but from the fact that it's a surface with topography, with undulations. And the consequence of that is that, use the display, is that the bending rigidity in this system grows, is scale dependent, and it grows as a function of length scale, and actually very strongly with an exponent that is almost 1. So the bending rigidity goes large the more and more kind of membrane that you want to bend. And so it stiffens. And you can illustrate that in the following way. If you take, for example, a piece of paper. A piece of paper is rather thin. It's very hard to stretch it, right? I mean, you can't stretch or shear. It basically has a two-dimensional shear modulus, which is infinite, or a stretching modulus, which is infinite. But it's so floppy that it can't even support its own weight. Okay? So this is the zero temperature version of this elastic membrane. But if you heat it up and you're trying to take a cartoon image of what a snapshot of what a thermalized configuration of such a membrane would be, it's kind of more like, it's got all these corrugations in it from thermal undulations. It's more like something like this. And now you see it can support its own weight. It's stiffer. And you can also shear it a little bit, stretch it, deform it by ironing out these wrinkles. So when you corrugate, say, cardboard, it becomes stiffer when you try to bend against corrugations. You can bend, like this, but when you try to bend the corrugation itself, it's quite hard. In this kind of system, you have corrugations, but they run isotropically throughout the whole system. So now, on short scales, you can have, this so-called microscopic bending rigidity of the system. That's fine. But for the membrane as a macroscopic object, you have to bend the whole thing, which means you're bending against all of these isotropic corrugations running throughout the system. And that increases the bending rigidity. And it's a field theory calculation to work out how this bending rigidity grows, but that leads to this result here, that that the bending rigidity grows almost linearly. This exponent eta is almost 1, grows almost linearly with the system size. So it's a very dramatic effect. Once you have scale-dependent bending rigidities, the theorems which tell you that the system always disorders are gone, because now you don't just have parameters there, but you have running coupling constants, if you want. So this follows from a renormalization group. The underlying message here is that this is not a two-dimensional system. You're on a membrane, you have fields living on the membrane, you have these normals, if you want, but a normal describes, and the mean curvature squared and so on, describes how the surface is embedded in the space it's living in R3. So actually the field is a mapping from a two-dimensional surface to R3, and that's fundamentally different from a pure field living on a two-dimensional surface where you only have to worry about the 2 dimensions. So it's a hybrid of a two-dimensional system and a three-dimensional system. It's a mapping, and that's the fundamental field relevant to the problem, and that's a very different kind of field. So you mix, a membrane mixes, physical membrane like this mixes 2 and 3 dimensions. If you actually do the field theory calculation and work out the flows of the bending rigidity, you find the following kind of structure. What controls the bending rigidity is a fixed point in the renormalization group flow, which is valid, which drives the system to this point here. It's an infrared fixed point. So this whole phase is a critically ordered phase of this extended structure of the membrane with long-range order in the normals. And this whole, no matter where you start in this phase, you end up here describing the properties of the thermalized elastic membrane. So this phase exists all the way along this line until you get to a point out here where the membrane can actually crumple and completely disorder. So this is stabilized by infrared fixed points. So infrared fixed points will give you this large range of parameters over which the structure survives. And you can do experiments on this system in the following way. Here's a picture, a detailed picture of this membrane. And really what you want is very thin objects. So if you look at the ratio of energy cost of stretching versus bending, then the energy cost of stretching is controlled by some two-dimensional Young's modulus, which is an energy per unit area, times the area of the system. Let's take it just L by L. So here has area L squared. And the bending rigidity is an energy. So you divide by the bending rigidity. Now you can get the 2D Young's modulus from a 3D modulus multiplied by the thickness. And you can get, it's shown on the next slide, the two-dimensional Young's modulus is a three-dimensional Bolt modulus times the thickness. This is energy per unit volume, so you need a thickness. Bending rigidity is the energy per unit volume, and you need 3 powers of thickness to make an energy. So it goes as thickness cubed. And so when you take this ratio, 3D Young's modulus cancels out, and you just get length divided by thickness squared. So as you go, it's purely geometrical. As you go to thinner and thinner things, they will become bending dominated. They much prefer to bend rather than to stretch. So the thinnest things you can imagine are, say, graphene, atomically thin two-dimensional materials. They will maximize this what's called von Karman number to maximize the dominance of bending over stretching, to maximize this kind of phenomena where it's all the configurations of the bent system that dominates its behavior. The other important thing is that to see the effects of these thermal fluctuations, which are build up at long length scales, you have to be above a certain minimal size. Okay? And this occurs in the following way. If you look at the renormalization group flow of the bending rigidity, it goes as some Beer value in a low temperature expansion as y kBt over the bare bending rigidity times something that's built up from the large distance fluctuations that grows as, let's call it L thermal squared, is the length scale at which this matches this. This is where the fluctuations make as important a contribution to the microscopic bending rigidity as the microscopic value itself. So if you compute this quantity, it goes as the bare bending rigidity divided by the square root of y kBt. Now, we always thought, I thought anyway, that we should see all these phenomena in very soft systems. Soft systems are good in that the microscopic bending rigidity is small, but they're not good in that the microscopic Young's modulus is also small. So this number can be very large, even bigger than the system size, like for a red blood cell membrane, for example. But for graphene has an atomic energy scale bending rigidity because it's just bending carbon-carbon bonds, but it has a very large Young's modulus. For stretching bonds is much harder than bending one against another like this. So this length scale for graphene at room temperature is order angstroms, or most nanometers. So that means immediately when you start, if you thermalize the graphene sheet, then you will see the effects of all these thermal fluctuations stiffening the membrane. And just to compare numbers, for red blood cell cytoskeleton, this thermal length scale is 10 microns, and that's bigger than the red blood cell itself. So you'll never see the effects of the thermal fluctuations. For paper, call it papyrus here, the length scale is 50 kilometers. So if you thermalize paper, you have to make a 50-kilometer sheet in order to see these effects. So this example here, thermalized, would have to be huge in order to see this effect. So this is a nice example where soft, I call it soft, fails, but hard wins, the combination of quantum mechanical bonds, giving you high Young's modulus, and the effects of the system being an elastic membrane. So you can heat graphene. These are the graphene parameters. This VK number is of order for typical sizes. You see, you can make, this T is angstroms, you can make L microns or tens of microns or hundreds of microns, so you can have 6 orders of magnitude easily here. So the square gives 10 to the 12. So it's completely bending dominated. Standard paper, by the way, is VK is of order 10 to the 7, so you do get the sort of intuition you get from crumpling paper is not altogether inaccurate. So Paul McEwen's group at Cornell, 2015, they released graphene in water, and you can manipulate it here with a manipulator, and it kind of looks like a cloth or a sheet, and you can push on it, and it will wrinkle up a little bit, and you can pull it back. And by the way, the electrons can flow, since there are pi electrons that flow above and below the surface, they can easily flow over a corrugated, over interesting topography surface, because they just follow along the surface easily, flowing above and below it. So these kinds of manipulations don't change the electrical conductivity of the system. They're almost immune to it. You can make them of all different sizes, and what they did is they turned these sheets on its side, bombarded with light, and they extracted the bending rigidity from the spring constant of the membrane. And they found that you can get a bending rigidity which is 70,000 times the microscopic bending rigidity, which is electron volts. And that corresponds to having, microns of material to work with over this fundamental thermal length scale of order nanometers or angstroms. So indeed, the whole thing gets very, very stiff. And then you can do, so we did a lot of theoretical work on this and simulations, and you can do interesting things like, this shows an intact graphene membrane compared to a membrane that's been perforated with a bunch of holes. A bunch of holes ones is shown in pink here, and the intact one is shown as blue. And when you punctuate it with holes, you have less material to bend, and you have new length scales that come into the problem, and you can get it even to fold over into, these are at the same temperature, fold over into basket-like shapes and even crumple. like this at much lower temperatures, even room temperatures. So the crumpling point, which is the far right critical point I showed you in that phase diagram, has never been demonstrated experimentally. And this should be the system to do it, perforating graphene. But the experimentalists have not yet met this challenge. So this is going to go the opposite way. Theoretical prediction that the courageous enough experimentalists should be able to verify. And one final interesting point for this system is a new kind of phase transition this system exhibits. So if you take a ribbon and you clamp it on one end, so it's like a diving board, which is actually the usual situation for cantilevers and metamaterials, nanoelectromagnetic systems, microelectromechanical systems, and so on, NEMS and NEMS. You want to, you have stuff where you've got to put in leads and so on. You at least clamp it at one edge to give some control over the system. If you clamp it along one edge, that means that with respect to the thermalized ground state of the free membrane, where the membrane likes to shrink, and it will have a shorter length across here, when you clamp it like that, you're effectively extending it compared to the right reference state for a thermalized membrane. So when you extend it like this, you're pulling on it. When you pull on it like that, you get a kind of a transverse response, because you pull on it like that, it likes to shrink like that, and it will like to sort of buckle, so-called Euler buckling in the transverse direction. But it's got a free end. So what happens is, with enough clamping, that means enough width, the system does the following thing. It spontaneously rises up, tilts up, so that's fluctuating about a non-zero tilt angle, and it can tunnel or fluctuate over the barrier between up and down, like a nitrogen molecule. And it's a two-state system with a non-zero tilt going from up to down and up to down. And as you go more and more into this tilted kind of phase, it'll stay longer in one than the other. So it's a clock, and you can work out oscillation rates and fluctuations across the barrier rates and so on, purely controlled by the geometry. As you have to heat it up a bit to get this kind of ordering I was describing, but then it's all controlled by the ratio of the width to the length. And you can work out a phase diagram for this system. So here's the degree of tilt as a function of sizes or aspect ratios. The aspect ratio has to be between like 2 and 5, so it's wider than it is long. And this describes all the phases where it's tilted. So this is another experiment that has not been done. It should be done. And there's probably even a zero temperature version of this experiment where you take an elastic sheet coming out from a wall and just pull on it like that, and it turns right or left. So that's another kind of spontaneous symmetry breaking, which is very counterintuitive, which is a combination of the thermal fluctuations ordering, the thermal fluctuations giving you preferred ground states, equilibrium ground states, with respect to which you have to work out the statistical mechanics. And finally, these kinds of problems are very, very widespread. So there are two, talking about in theory, there are two really important ideas in theoretical physics. One is quantum mechanics. Okay? Who believes in quantum mechanics? What? Only so few. Who believes in statistical mechanics? That's another. One of the most fundamental ideas, often somewhat neglected in 20th century, 21st century physics. So one gives kind of unitary evolution of quantum states, right? And so it's very, very different. It's kind of, go pure state to a pure state. It doesn't mix. The entropy is like minimized. The statistical mechanics will tell you that ultimately the entropy should be maximized, should go to a completely disordered state, and so on. So, I believe in quantum mechanics. I believe even more in statistical mechanics. So, are these two compatible? We're going to give up one or the other. Should a quantum system thermalize and obey ultimately statistical mechanics or not? Who thinks quantum systems should thermalize? Okay, that's good. So there's a beautiful paper by Sunwon Choi out of MIT very recently. He gave a talk at KITP and he asked this question. So I'm borrowing from him. And one person said, I think the quantum system should always thermalize. Of 120 something people, and he said, I agree. And then he had a beautiful talk where he showed the conditions under which a quantum system must thermalize. Okay? And so it's a work in progress to find all of the conditions under which this must happen. But in a certain set of very reasonable conditions, it always must thermalize. And the point is that you have to really pick out from an ensemble of pure states to sort of begin with. And once you have that ensemble of states, you can reach a thermalized configuration. But how systems disorder, their response to various kinds of noises, all fit in the same framework. Soft condensed matter systems, active systems, hard condensed matter systems, quantum systems that have to thermalize and so on. They're all subject to these ideas of symmetry breaking, of creating maybe order from disorder, of stabilizing structure and having structure originate, and what happens at large sort of times for these systems. So I think it's a very, very general and exciting area that will combine all these areas of physics. So, thank you.
All right, thank you, Mark, for this wonderful presentation. We are a little bit over time, but on the other hand, the quantum mechanics in this system thermalized on us a little bit too much. Maybe a few short questions before we wrap this up. Anyone has some more?
Yeah.
Sorry, I have a general question.
Go ahead.
You mentioned, at the end, you talk about decentralization in
Yeah.
quantum systems. My
Yeah.
question is, does that have any implications for quantum computing, any particular topological quantum computing? And like also, you are talking about this, but I know this is kind of like a big field of like towards quantum computing side
Yeah.
of things. So does it mean that we can never really stabilize the topological like qubit and stuff like that?
Yeah, so in all those systems, topological or not, as I said, you design, for example, one fermion, like one direct fermion has 4 degrees of freedom. And therefore, you need to map it onto 2 qubits because they have just 2 degrees of freedom, right? So you need 2 qubits. And then you need to figure out the physical array of the qubits. And so you're mapping from the spin systems onto a physical layout of qubits, which they do through codes and so on. Now, if your spin system doesn't have any order whatsoever, that won't work, right? So you want to have this order be preserved for at least some range of noise in order to prevent decoherence. So that part is very general. You want to preserve that structure as much as possible and not lose it right away by decoherence. Now, if you go to topological computing, many different things come in. First of all is the topological behavior itself, which, by the way, is also a huge expansion in our notions of symmetry breaking, because now we can talk about an ordered state, a regular ordered state going to a state with topological order, a disordered state going to a state with topological order, a topologically ordered state going to an ordinary disordered state, and so on. All of these different kinds of phase transitions now are relevant, and they are mostly related to various kinds of entanglement occurring. So that also is enormous expansion in this idea of symmetries and symmetry breaking. Now, topological computing relies on basically objects like anyons that have their own kind of topological stability. But topological objects, even though they have topological invariance, you can destroy topology over finite times because in the evolution of a dynamical system, it can develop singularities in finite time. So even an anyonic system with noise can lose that structure, which guarantees the quantum computing stability of the system, preventing it from decohering. So it's very relevant there also.
Okay, so you just so you're
Yeah, no.
saying that even because you lose this like quantum feature in finite time, as you just said.
You can do, yes.
So you will still need error correction of some sort.
Yeah.
To make okay.
Yes. Yeah. Other questions? Okay, well, I think we had questions during. So. Yeah.
What are the systems that you are most excited about?
Me? A bunch of them. So if you take these soft condensed matter systems, but you make them locally consume energy, the so-called active matter systems, then all the problems that you have a new source of noise. You not only have thermal fluctuations, but you have dissipation at all local length scales. So those are kinds of driven systems, but they're locally driven as opposed to being driven from the boundary. And yet it's not actually clear if there's a real difference between driving something from a boundary once you have communication across the material from actually driving it locally. So this relates this kinds of thermalization of quantum systems to ordering in soft condensed matter systems, and even in systems of biological development where you have all kinds of noise coming in as well, like cell division, lots of other things. So I think all of these things are all kind of related. So if I that's what I dream about, after midnight, or after a beer.
Great. So let's thank our speaker again.